Good morning. My name is Maxim, and I'm a graphic software developer for Simmakers. I would like to tell you about the most up-to-date graphics technologies for creating 3D effects in movies and animations. Everybody likes to watch movies. Modern movies are very spectacular and full of various visual effects. How are these effects made? Generally speaking, in order to generate a whole picture, we use an approach called compositing. According to the definition taken from Wikipedia, compositing is a combining of visual elements from separate sources into single images, often used to create the illusion that all those elements are part of the same scene. For example, pictures can be taken, processed in 3D, rendered or obtained by means of other possible variants. Compositing itself probably dates back as far as the trick films of Georges Méliès in the late 19th century. Compositing in movies could be used, for example, to replace backgrounds and overlay monsters. Also, compositing is used in computer games in order to combine the results of multi-threaded rendering, i.e., some independent graphics output, some large objects, etc. As you can see on the right picture, there are 5 lookalikes. This is a result of compositing. It means that we have filmed the same person from different angles and inserted his picture in various frames. We can also use rear screen projection when it's impossible to shoot on location, or if we are creating a science fiction movie and we need to have Mars as a background. We can do this with the rear screen projection method. The main goal of the rear screen projection method is to prepare scene backgrounds in a separate process. For example, the background for a driving scene. In this case, it is just an imitation. In order to create a sequence like this, the driving scene is prepared in advance and the car is filmed in the studio. Then the road is projected onto our background video. It's Bill Gates. These methods have evolved a lot recently and are used very often nowadays. Let's talk about chroma keying. This is when you see a green room or a green background during filming. The object of the scene in this case consists of the character and a green background. The green background can be substituted with anything. For example, a weather chart, a space background, battle scenes, etc. In addition to chroma keying, there are other alternative methods. For example, it isn't necessary to use the background of the same type. We can instead superimpose an image onto the existing one. To do this, we need to create a 3D model that will interact with the movie character. In this example, Daenerys' dragon interacts with her very realistically. It throws shadows on her and hides behind the girl's hair. Moreover, it isn't in front of the girl, as it would have been if we had superimposed 2 pictures on each other. Such composition is also suitable for animated cartoons. Let's consider the Puss in Boots example. This scene is composed of different elements, separately rendered sand, background, bridge, and many other things. In other words, all the scene elements were computed separately and then were rendered and compiled together. The sand is rendered separately because it's necessary to simulate or calculate some physical processes, and ray trace everything separately because all the grains aren't the same. It is a very difficult process. How is it all done? One can use hardware, software, and coupled systems. A mixer is an example of the hardware approach. An example is when a studio technician moves control sticks and presses the buttons, resulting in the green background changing to something else. As for the software approach, I would list, for example, Adobe After Effects or the Foundry Nuke. These programs are powerful enough to create special effects, such as chroma keying or the insertion of 3D objects. The Foundry Nuke is particularly powerful due to the fact that it supports both rendering and shading. Coupled systems are very serious solutions. For example, RenderWall integrated with rendering software and GPU acceleration. This is a very interesting, advanced, and highly demanding field of study. Shading is also used in the field of visual effects. I think that most people know what shading is. It's a process of changing the color and lighting parameters of the resulting picture. Software used for these purposes are called shaders. There are special programming languages for creating shaders, one of which is Open Shading Language, which we encountered in our projects. Open Shading Language is an open source project developed by the open source community with Sony ImageWorks. It is also a very powerful system which interacts with renderer, and Open Shading Language has a good integration into it. But still it has one important limitation. Due to the very strong internal data interactions with the renderer of this system, it was only developed for CPU, i.e., it can only be parallelized as MIMD, multi-threaded on clusters. Everybody knows OpenGL library. It contains GLSL language. It is a standard for high-efficiency rendering, as well as OpenGL. It is a very serious technology on which many visualization systems are based. In most cases, it is used for rendering. The main distinguishing feature of GLSL is that it is targeted to GPGPU. It means that GPU can execute instructions for all the data very quickly. If we give a command to take a texture, the command is executed by thousands of flows simultaneously. If we give a command to multiply, it multiplies simultaneously in all these thousands of flows. In Open Shading Language, it would require 100-500 cores and 100-500 accesses in order to have the same effect. Unfortunately, it is impossible to transfer it to GPGPU. We wish we could because the system is rather powerful. We came across this problem once when our customer asked, "Why don't you transfer OSL to GLSL? These languages are the same." Actually, they are not the same. Their syntax may look similar, the approach is also similar, but OSL, in contrast to GLSL, uses CPU for code execution and simultaneously uses various shaders in any configuration. In the end, I would like to say that demands of cinematography are constantly rising, and this gives us the impetus to develop this highly specialized branch of computer science. Thank you for your attention.